We will now consider what are commonly called as equations of fluid motion. You can call it, they are the governing equations of fluid motion. Eventually, the governing laws are nothing but the statement of the physical conservation laws. One of these physical conservation law we have already considered and discussed, which talk about conservation of mass, and we have derived the mass conservation equation or equation of continuity. Just to remind you once again, mass conservation, that is the first equation, and if you remember that we consider 2-3 approaches to derive this equation, in which in one case we considered a control volume and then found how much mass is entering that control volume and leaving the control volume, and the difference of that is the rate of change of mass within that control volume. Okay. For that we consider, say, a cubic control volume, and we consider each phase how much mass is entering. That is the way we did it one case. We also used a straightforward vectorial approach, by which we found out the total flux of mass out of that control volume, which again we equated with the rate of change of volume, rate of change of mass within the control volume. And the third alternative that we consider, that we consider a material volume, that is a volume which is not fixed in space, but a volume consisting of or comprising of certain amount of fluid. Then we said that the volume of that material element can change because of the movement of the boundary, how much the boundary is moving, and that is the way we found out the rate of expansion or dilatation. Of course, the equation is same in all the approaches, and the equation, to remind you once again, is d rho dt plus divergence of rho u equal to 0, or can be written as like this, d rho dt plus rho divergence of u equal to 0. In index notation, this also we wrote that d rho dt plus rho d u I dx I . So, this is a different form of conservation of mass, popularly known as equation of continuity or continuity equation. And from here we said that for an incompressible flow, in which the change in temperature is also not large, change in temperature is also small, so that density remain constant, the equation of continuity simply becomes divergence of u equal to 0, or divergence of u is the dilatation or rate of expansion. So, rate of expansion is 0 is the form of continuity equation for incompressible fluid. So, for incompressible case, right, in particular, I will ask you to recall that we also defined that rate of change of the material volume rate of change of material volume tau. Tau is the material volume, that is volume comprising of certain amount of matter, certain amount of fluid, not just a volume in space, is sorry not divergence, or okay, in terms of divergence write both. In terms of the movement of the boundary, where this S is the boundary of this same material volume. So, this is the amount by which the boundary is moving, which can be written as and we defined that rate of dilatation rate of change of material volume per unit volume is divergence of u. Rate of change of volume per unit volume is the rate of expansion. So, divergence of u is the rate of expansion or dilatation, which of course, we have done earlier. We need this for our next equation. So, that is why I just wanted to recall this. The second conservation, or which now we set to derive, is the conservation of momentum, which is of course known to you in the form of Newton's second law. So, eventually that is what gives the so called equation of motion or governing equation, conservation of momentum. What it says, that it relates the rate of change of momentum with the force acting. Now, when we discuss about rigid body mechanics, these are more or less obvious, that rate of change of momentum. Rate of change of momentum of what? Obviously, of the particle or of the body. In rigid body mechanics, there is no ambiguity. But when we come to fluid mechanics, because of our nature of description of the fluid motion, we have little ambiguity. Rate of change of momentum of what? So, you have to be very clear that this is the rate of change of momentum of the material. Okay. Rate of change of momentum. So, in case we are using the Eulerian description, where everything we fixed in space, a volume, a fixed volume in space. The material is not fixed, the volume is fixed. So, obviously, the material, since the material is not fixed, the rate of change of momentum of that volume is really not applicable in this context. What we need is rate of change of momentum of certain material fluid. Okay. And similarly, the force acting on it. So, let us consider a small or infinitesimal material volume, infinitesimal material volume. Then what will be the momentum associated with it? Let us consider a material volume material volume element, we are calling it delta tau. So, how much is the momentum associated with this material? Rho u delta tau forward. The mass of this material element is rho delta tau, and so momentum is into u. Of course, integrated over this entire volume. Sorry, rho u dt integrated over that volume element delta tau. Now, the rate of change of this however, we already mentioned that see this description of fluid motion based on material is not very convenient, is not very suitable. The description based on the control volume approach or point approach, field approach is more convenient and is more widely used. So, this will now shift to that control volume or volume based approach, and you see how that we obtained. This we can write this u, the way we have defined is that Eulerian description. The velocity is described by Eulerian description, that velocity associated at a point. Okay. So, this derivative is basically the material derivative. Here we have derived it on the basis of the material. So, to look for the derivative of the velocity, this is basically the material derivative, and we will use that same notation, that this is now become this. Is that all? No. You see, even this, the material volume, that is also changing. The material volume, that is also changing. So, we have even this integration. Okay. And now, replace this by using that relation here, using this by the rate of definition of rate function. this we can further write okay. Okay. And see the second term is 0. This term is 0 by equation of continuity. Okay. The second term is 0 from the equation of continuity. So, we have only please look to this particularly carefully, because this is a question of perhaps again we will hear from you many times, that in this the density is out of the derivative term. So, okay, perhaps again you will say that okay, this is valid when the density is constant or say for incompressible flow. But you see it is not so. We have started here where the density is taken within the derivative, only it has become like this. So, here even though this density is outside this derivative sign, we have never considered density to be constant. It has become 0 because of this continuity equation, and this continuity equation you can see is valid when density is variable, because in our final equation this is what will remain, where you will not see that the density is being differentiated throughout the equation. So, most of the time you try to believe or you think that this is an equation in which density is taken as constant, but no. See, the density has been taken as a variable, only because of this continuity equation this has taken this form where density has come out of the derivative. Okay, this rate of change of momentum, as you know, is balanced by the forces that are acting on the fluid element. We have already discussed a great deal about the forces that acts on a fluid element. and what are the in general. Okay, in a specific case we will have specific forces, but in general case the general forces, the body forces and surface forces. Okay. So, we can write what is the body forces acting on the fluid, that can straightaway be written body forces acting on the fluid. Once again, if we follow the same notation, that F is the body force per unit mass, F is the body force per unit mass, then the total body force is okay. And how much is the surface force acting on it? This you have done already. The amount of surface force remember, surface force acts as a tensor, force per unit area acting over the entire surface. So, the surface force is how much? Of course, in this case we cannot use the vector notation alone, the conventional vector notation we cannot use now, we have to use the tensor notation. And the if sigma I j is the stress tensor, then where S is the or delta S is the surface of the material element delta tau. Stress is force per unit area. So, you are multiplying by the area which is normal to a particular element of stress. And this by divergence theorem, this divergence will be on the second notation, this will be the divergence will be written as this. So, now we can write the conservation of momentum. So, conservation of momentum gives since you have been forced to use this index notation for these terms, let us use that index notation for all the terms. The vector is by this. Okay. All the integrations are over the volume material volume element delta tau. The equation is true for any arbitrary volume element. Hence, we can remove the integral sign and the equation holds. The equation is true for any arbitrary volume element, and from there we can write so the most general form of the equation of motion. However, you see that the equation in this form is perhaps not that useful unless we know little more about the stress tensor, particularly how the stress tensor is related to the motion. How the stress tensor is related to the motion. Unless we can specify that, this equation cannot be used. This equation cannot be used. As far as the body force is concerned, you see the most common cases, the body force is the gravitational force, or you can write that F I is the g, gravitational acceleration. In some problem, if there is different type of body forces, usually you will be able to write what is that body forces. If it is electromagnetic body forces, it will come with a cross product with the velocity and magnetic field, electric field multiplied by the charge. So, that sort of force terms will come if there is any other type of body forces like electromagnetic, or if you have some centrifugal type of fictitious body forces, that also you can write in a specific case. But we must know something about this stress tensor, how it is related with the motion in general. Until we can do it, there is no question of solving this or doing anything with this equation. However, before we go to look for something about this stress tensor, we will try to write this equation in another form. We try to write this equation in another form known as in integral form. Of course, you can say that you have already derived in integral form, but we will now do it. Rather, we will write this equation in another integral form. See the first term here, this d u I dt, as you know that this material derivative can be written in this form. Now, this time we will integrate this equation, while writing this equation in integral form, we will use volume element which is fixed in space. That means, we are not going to consider material volume element, but spatial volume element, because you see in a practical case that is more convenient. In case of a fluid motion, considering of material volume element every time where that material is going and tracing it, instead of that, if you have a fixed position, fixed volume, that is more convenient in any problem. You think about just a problem volume, that is all, forget about what is the matter. So, if we now integrate over a volume element which is fixed in space, this equation becomes as before. We are using the tau for material element, V for volume spatial element, volume fixed in space V, volume of material tau. To write this equation, we use the divergence theorem. We change it from a volume integral to surface integral. What it will be? This term will also be integrated over volume, but that volume integral we want to write it in terms of surface integral. Where A is the surface bounding this volume V. This is the momentum flux across the surface, the momentum flux across the surface. The last integral, again there we will change this volume integral to surface integral. So, d sigma I j d x j d v, what it will become? We already had it, sigma I j n j d a. Now, consider a steady flow. Consider a steady flow, so that the left hand side becomes 0. Okay, you can write the equation for unsteady flow also, but the steady flow it will become more useful. The left hand term drops. And also in particular, consider the body force is a potential force. Okay. And in addition, also if we consider the density is uniform, in particular if the density is uniform, then this term again can also be written as a gradient term. This we did earlier. Then this equation will become so, this is the integral form. Of course, we have some additional assumptions, that is, we have assumed the flow to be steady, we have assumed the body force is potential and the density is uniform. But you see, none of these assumptions are too restrictive, because these are in many cases, many common cases, the flow problem is like that. The flow is steady, the density is uniform and the body force is a potential force. So, even though some additional assumptions are incorporated here, they are not too restrictive. The advantage of this integral form is that if in a particular, if in a specific problem you can apply integral form, you get the solution very easily, almost without doing anything. Okay. It does not give the details. The integral form will not give you the detail that velocity, pressure at each and every point and so on. But in many problems really you are not interested in that, or the most interesting thing is not the velocity or pressure at each and every point, but at certain important situation, which you can very easily get it, particularly if you are in a position to apply integral form. I think I will consider one simple numerical problem. Think about a jet coming out of a nozzle, let us say a nozzle. From this a jet of fluid is coming out, okay, and this jet of fluid is hitting a plate. Okay. As you can understand that this jet of fluid will try to displace this plate, it will exert certain force on it. So, if you want to keep it fixed, you have to apply the opposite type of force. How much is that force? Consider, say the diameter is 10 centimeter and the velocity here is just 8 meter per second. The velocity, it has only one component of velocity, the x component, we will call it say u1 8 meter per second. You can consider a control volume like this, and apply this momentum. And apply this momentum equation in integral form, and you will get the force or the solution straight away. In this problem, of course, we can neglect all these viscous stresses. Sorry, we should not call viscous stresses at this stage. Okay. That stress, there is no stress acting on it. What happens when this jet hits the plate? Remember that jet splits into half, it follows the plate. So, there will be flow in this here after coming here. When it hits the plate, it can no longer go in the straight direction. So, it will go up and down following the plate.
Particles rebound. Particles can rebound also from the surface.
No, see, in this case rebound means that they will be again carried. This flow is continuous, no? So, they cannot come back this way. This flow is going continuously. So, a particle cannot come back. It will be again taken away by other particles. So, in this problem, see, this I and j cannot take 1, 2, 3. We will treat this problem as a 2 dimensional problem. We will treat this problem as a 2 dimensional problem. So, I and j both can take 1 and 2. And eventually that rho into u1 that gives the into area, of course, gives the mass flow rate. The mass flow rate rho u1 into this cross sectional area, that will give you the mass flow rate. Yes. See, the force acting on the fluid, can be obtained from this just by writing the left hand side term only. Okay. The right hand side, whatever is there, that is the force acting on the fluid. So, that can be obtained by writing only the left hand side terms only. So, how much is that? Rho u1 a. Now, this u2, that is the velocity in this direction, there is of course, but in that there are both terms. Upward as well as downward. However, both are same. Yes, both are same. If you take this area, of course, here is an assumption that the fluid is split in two half exactly. But of course, there is no reason why it should not be. Anything else? Yes, also in this direction is there rho u1 a u1. What will be the sign of this term? For if we consider force acting on the fluid, then it should be negative. If we consider force acting on the plate, then it is positive. So, actually this is what is the term. Ultimately, this is what is giving us everything. So, force on the plate u1 and u2. Sorry, this is one is in the upward direction, the other is in the downward direction. I perhaps not following you.
So, we took all the combinations u1, u2,
u1,
u2 again, and then u1, u1.
Huh.
Why didn't we take u2, u2?
u2. No, see this part, if you write this equation, this I in the direction of x, we are writing only in the force in the x direction. Okay. Force writing in the x direction, this I actually gives the direction. As you can see, this j is summed. Okay. J is repeating. So, j mean this, it will be sum over j. So, actually this I will remain in the final equation. Okay. In each term you see this I will remain. So, this is an equation in the I direction. We are writing here the equation in the x direction, okay, or the first one direction.
Psi is the potential function.
Psi, okay.
Is the velocity potential, right?
No, this is not velocity potential in this case. This is the we said that the force is a potential force. So, it is a potential force. So, in this case this psi do not treat it as a streamline. Okay. Please do not give much weightage to the symbol itself. Look what that symbol stands for, that whenever there is a psi, the psi is streamline. No, in this case the psi is not streamline, it is that force potential. So, rather it is a potential energy. Per unit mass. Okay, the numerical figures are not important, that can be obtained. So, this is the utility of these integral form. In any situation, wherever you will be able to apply integral form, you will see that the answer is obtained almost without any effort. But as already mentioned, that you will not get the details of the flow picture. You will get the important information without getting the details. This is of course one simple example, but there are many applications. You can consult any standard textbook on fluid dynamics and they will give you the application of momentum principle for various numerical problems. Perhaps we will also give you a few more problems as tutorial problems, which you may try. Okay. Then I think we will stop and discuss about the stress tensor in the next class.